When you think about ceramics, your mind probably goes to a coffee mug, right? Or maybe a dinner plate. They're hard, they're strong, but they're incredibly brittle. You drop one, it shatters. End of story. But what if I told you that under the most extreme pressures you can imagine, these exact same materials have a secret life? They start behaving in ways that are just bizarre, totally counterintuitive, and absolutely critical for protecting us from some serious stuff. Okay, so let's get right into this fundamental difference. You hit a piece of metal with some serious force, its atoms can kind of slide past each other. It bends, it deforms, but it stays in one piece. Now, a ceramic, its crystal structure is super rigid. There's just nowhere for those atoms to go. So all that energy has to be released somehow, and boom, it shatters into a million tiny pieces. And right there, that's the central paradox, isn't it? If these things are basically designed to shatter, why on earth would we put them on the front line of our most advanced body armor and military vehicles? You think that's the last thing you'd want? Well, the answer is way more complex and, frankly, way cooler than you might think. To solve this mystery, we've got to look at what happens in the first billionths of a second of an impact. It's just an unbelievably small window of time. So our investigation starts with the most obvious failure: cracking. But as we're about to see, it's not just simple shattering, not by a long shot. Scientists have a name for this threshold, this point of no return. It's called the Hugoniot elastic limit, or HEL for short. Up to this point, a ceramic can take a hit and it'll bounce right back, no problem. But the second you cross that HEL, the material structure begins to permanently break down. There's no going back. And this limit, it is astonishingly high. For a tough, armor-grade ceramic like silicon carbide, we're talking about 15 gigapascals. To put that in perspective, that's a pressure of nearly 150,000 times the Earth's atmosphere, all concentrated on one tiny spot. It is an absolutely immense force. And that's just where the failure begins. And here's the thing, exceeding that limit is actually what allows the ceramic to do its job. It kicks off this whole web of tiny micro cracks that spreads the impact energy out over a huge area, basically blunting the tip of a projectile. But if that were all that was happening, it wouldn't be nearly effective enough. There are deeper, much stranger things going on inside that material. And this is where things get really weird. Under that intense shock, some ceramics don't just break. They literally change their identity. They transform into something else entirely. The process is called a polymorphic transition. Just imagine all the atoms in that ceramic's crystal lattice, right? They're perfectly ordered, like soldiers on parade. Then the shockwave hits, and in an instant, they are forced to reorganize into a completely new, much denser formation. This very act of transforming absorbs the projectile's energy. It literally steals its momentum. And to give you an idea of just how fast this all happens, look at what happens to quartz. When it's hit by a massive shock, it transforms into a new, dense mineral called stishovite in about 10 nanoseconds. But it can't even hold that new form. Just 30 nanoseconds later, as the pressure releases, it completely collapses into a disordered glassy state. A total transformation and then collapse, all in a few billionths of a second. It's just mind-boggling. So this leads us to what is easily the most counterintuitive failure mechanism of all. See, this isn't about the material cracking from the outside in. This is about the material collapsing from the inside out. While they were studying boron carbide, which, by the way, is one of the hardest materials known to man and a key component in body armor, researchers noticed something deeply troubling. Under shock pressures above a certain point, it would suddenly lose its strength, specifically its shear strength, which is its ability to resist its own internal layers from sliding past one another. It went from being super hard to, well, weak in an instant. This was the big puzzle. What in the world could cause a material that's famous for its hardness to suddenly fail so completely? It wasn't cracking in the normal sense, and it wasn't just a simple phase transition like we saw with quartz. It was something else entirely. The answer is a process called amorphization, and it is wild. The shockwave becomes so intense that the perfect crystal structure just can't hold itself together anymore. It literally collapses in on itself, forming these tiny, localized bands of glassy, disordered material. These bands act like liquid layers inside the solid, allowing the material to flow and erode an incoming projectile, grinding it down like microscopic sandpaper. So, look, The whole point is that understanding all of these bizarre ways a ceramic can fail, the cracking, the phase changes, the amorphization, it's not just some academic exercise. It has massive real-world implications for how we protect ourselves and our technology from extreme forces.
This knowledge is absolutely vital. It lets us design better body armor and vehicle armor that can defeat more advanced threats. It helps us build shields to protect satellites from those little micrometeorite impacts up in space. Heck, it's even used in geophysics to understand the immense power of ancient meteorite impacts by looking for telltale signs, like that shocked quartz we talked about, right in the rock. All of these applications, from a soldier's protective plate to a satellite whipping around the Earth, they all share one common goal, using the strange physics of ceramic failure to absorb and dissipate catastrophic energy, all to protect the valuable thing that lies right behind it. But, like any great scientific frontier, the more we learn, the more we realize just how much we don't know. Unlocking the secrets of amorphization and phase transitions has really just opened up a whole new set of questions for scientists and engineers. We're definitely not done here. So right now, researchers are racing to answer these critical questions. Can they pinpoint the exact trigger for amorphization so they can actually control it? Can they measure precisely how fast these transformations happen so they can build better armor? The ultimate goal here is to create computer models that can finally predict all this bizarre behavior, and to understand how tiny little details in a ceramic structure, like the size of its crystal grains, can change everything. And that leaves us with one final pretty fascinating thought. We spent this whole time talking about failure, right? But what if we've been looking at it all wrong? What if we could perfectly engineer these failures, the cracking, the phase transitions, the amorphization, to create the ultimate shock absorber? A material that is literally designed to sacrificially destroy itself in the most efficient way possible, all to guarantee the survival of whatever it's protecting.